Okay, so now let's look at the spreadsheet. As described, this spreadsheet is linked from homework 2F through the Euler worksheet link. Once you get to this page, you will see a template that I've constructed. To work with it yourself and edit it, you'll need to go to File, make a copy, like that. Give it a different name, save it where you will, and then you have your own copy to edit and work with. So this spreadsheet is demonstrating examples 2.6.1 and 2.6.2 from the book. Let me change that real quick. Okay, so first, the differential equation we're solving is x prime equal to t minus x and x sub 0 equals 1. Now this is a linear differential equation which can be solved. We've looked at similar problems before, and we'll be using an exact solution, a solution to this differential equation to compare our numerical methods. But the real power behind numerical methods is when you can use them to solve differential equations that no other method can. So I did mention earlier that the exact method is the most general method for solving first-order differential equations. Well, the Euler method is even more general, except it doesn't solve them. It approximates them. So we lose that little bit. Instead of being able to find what the function is, we can at least graph a good estimate of that function most of the time. So that is the most general kind of method. It's not a solution, but it's an approximate solution and can be used fairly well for analyzing a number of differential equations. So let's dig in a little bit. First, look at some of the parameters we've set up. We have the number of intervals, n equals 4, and that's used to calculate the time step, delta t. In example 2.6.1, we're going from 0 to 2. And so we take the difference, the width, 2 minus 0, divide by the number of intervals we want, and then we get a delta t of 0.5. Initial condition, x of 0 is 1. Okay. So we set up our time to start at 0. We set up our approximation to start at 1, our initial condition. We set up our slope function to follow the differential equation. So in this case, it's t minus x, or a13 minus b13. And then as you scroll down, it compares those. So when you're solving another problem, change the slope function here, and you can keep the other values the same. If you do know the solution to this differential equation, type it in here. And for this problem, I mentioned it's linear, can be solved. Uses integration by parts. I think we did a very similar example in class, or possibly the same one. Very, very close. Okay. So I type in the solution, which is t minus 1 plus 2 times e to the negative t. As you expect, the t is from the column A, and then so is t showing up in the first, and then the exponent is both from column A. And then the error is computed by the true minus the approximate. So the true solution value from D minus the approximation from B. And then you scroll that down. So once you have all the values updated, here we go to the functions, you can scroll that down. Again, the main thing you're changing, if you were to update this to solve a different problem, is the slope function itself, the exact solution, and maybe some of these, the dt and x sub 0. The rest of it should run on its own. Boop. You'll notice that the form of the equation is written out above a lot of these. So x of j plus 1 is equal to x of j plus dt times the slope function. Well, x of j is just a previous value. So B14 is equal to B13 plus dt in B8. Notice in B8 I have the dollar sign to keep that dt, that delta t, fixed as I scroll down, times C13, which is right next to it. Okay, so that's Euler's method. Pretty straightforward to implement it. Now let's look at the improved Euler's method. What changes? Well, first, we have the same three columns we had before. The approximation, the initial slope, but then we add a few more pieces to find the other slope m1 and then average the two slopes. So first I predict what Euler's method would tell me. So that's the same value we had in the previous columns, but I'm only using that as a prediction, the next prediction. And then from that prediction, I calculate the next predicted slope. And then once I have that predicted slope, I average my original slope m0 and this next predicted slope m1 and find some balance between the two, which gives me my average slope, next average slope. That next average slope then can be used to calculate the corrected approximation here. So notice that we're multiplying delta t by the L column, which is our next average slope, previous value. So that's the main difference. Again, we're comparing to the same solution, and then calculating the error from the known minus the unknown. Now, this is set up initially for 4 intervals, and once you have it all updated for your problem, you can change the number of intervals and see how it changes. But first, let's look at the graph. So here we are graphing the solution in yellow, or gold if you rather, the approximation by Euler's method in blue, and the approximation by the improved Euler's method in red. Okay. And a quick check for x of 2, or x when time equals 2. We'll go along this row. For the Euler method, we have an error of about 0.15. And for the improved Euler method, we only have an error of about negative 0.03. So a third of the error, essentially. So now, let's double the n, which will cut our dt in half. Notice that I've set it so that the n's are the same, corresponding to this left one. If I go down to the row that has t equals 2, check my error again. My error for the Euler method went from about 0.15 to about 0.07. So it cut it in half. I cut the time in half. My error gets cut in half. And like I said, it's first order. The error grows proportional to delta t. So if delta t gets cut in half, the error gets cut in half. Now let's check the error for the improved Euler method. Originally, or previously, it was negative 0.03, sorry, negative 0.03, and now it's down to negative 0.007, let's say. So, if we divided it, okay, so that's not quite dividing by 5. It's actually pretty close to dividing by 4. 30 divided by 4 would be 7.5. So it's a little bit less than dividing by 4. Okay, so you can see that cutting the time step in half for this second order method cut the error in about by 4, maybe a little bit more than 4. And if we keep doing that, let's say n goes to 16. Scroll down to where it's 2. Our error for the Euler method continues to be cut in half each time. It was 0.06 last, now it's 0.03. For the improved Euler method, it's down to 0.015. It was about 0.007. So to get down to 0.005, we've essentially divided by 4 again. So think like 0.08, it's a little bit less than 0.008, and this is a little bit less than 0.002. So essentially divided by 4 one more time. So the order of the method, or how we describe the error, depends upon how many pieces of the original Taylor series we can match. And that averaging of the two slopes is one way to match higher derivatives. Even though it doesn't look like we're using a higher derivative, by using the D field and matching more of the slopes in the beginning, at the end, maybe in the middle, like the Runge-Kutta method does, you can find a better balance between the various values of the slope field, and that allows you to match more precisely higher and higher derivatives in your Taylor series expansion. Now again, this is something that we go into in more depth in a numerical methods course, but I just wanted to point out the difference and why a higher order method, numerical method, is so much more efficient. You get more bang for your buck, a lot closer to the exact solution, the solution for just a little step size change. Okay, and then let's check on your solution here. This one's showing, again, the yellow is the solution, the blue is the Euler approximation method, and the red, which is barely discernible behind the yellow, as your improved Euler method. And as you can see, graphing over just the time interval from 0 to 1, the blue is quite a ways farther away from the solution than the red. The red's very close, very close. A great and improved approximation of Euler's method. So that's our demo for today. Again, the takeaways from Euler's method is, one, knowing visually how the approximation uses slopes, being able to follow the slope field, being able to track that on D field, and then being able to estimate some values by hand by just using the algorithms developed for the Euler's approximation and maybe for the improved Euler's approximation. And since we're talking about it, let's look at the D field. Because this software is actually built off of numerical methods. So let's analyze it a little bit more. Let's take t minus x and graph from 0 to, let's say, 2, and x going from 0, I'm not sure how far we should go. You want to use the initial condition of x equaling 1. Okay. So there is an approximation. Now, what kind of approximation is it? We talked about Euler's method. We talked about improved Euler's method. If you go to options and scroll down to ODE solver, you can see what kind of numerical methods this D field applet can use. And the one that's selected by default is called the Dormand-Prince adaptive step, which is a 5th order averaged with a 6th order numerical method that's built upon the Runge-Kutta framework. It's a lot more complicated than what we're talking about here. But to get an idea of how it compares, let's scroll this back to Euler's tangent method. And let's choose a step size of 0.25. Let's apply. And then let's go back to a solution, input our initial condition, and you can see how the Euler's method with 0.25 compares to our Dorman-Prince method, which with whatever delta t they have listed, and the error it accrues. Now, one of the other option was Runge-Kutta 2, or otherwise known as the Improved Euler method. So go back, try this one out. Do another 0.25, apply, go back, solve. And if you can just barely see that, the Improved Euler method almost overlaps the Dorman-Prince, just a little bit off here and there, but is substantially better than the Euler method. Now, I may sound like dissing Euler method a little bit, but everything that we've analyzed since Euler's time has been built upon his method. It's the foundational method, the first numerical method that was developed, and it is fundamental to every way of approximating differential equations. So it is the kind of bedrock method, Euler method, and from that bedrock we can build a little bit more and we can improve upon it. So that will conclude our demo of numerical methods.